So the last method for finding derivatives um, is called automatic differentiation or algorithmic differentiation. Um, it's actually very similar to analytical differentiation in a sort of conceptual sense, except this method does not carry explicit analytical expressions for the derivative. No explicit expressions are generated, and it doesn't sort of carry the expressions around as we try to compute the derivatives. Um, Instead, what happens is sort of roughly, given a computer program for computing, say, f of p, the underlying software, say MATLAB or an automatic differentiation toolbox, what that will do is essentially generate uh, effectively either another program or another sort of sequence of steps that generates the derivatives of f with respect to p. And it does that by essentially implementing the chain rule of differentiation on every line of p. So f of p would be perhaps a few lines long. And how do you compute the derivative of a function with respect to another variable? You just apply the chain rule for each function operation that we do, essentially, right? Because any function f of p is going to be some combination of basically elementary operations like addition, subtraction, multiplication, division, simple functions like sine, cosine, tan, cotangent, and so on. And we know how to propagate derivatives through such simple functions and elementary operations. It's just the chain rule, and we know the rules of differentiation for each of these functions. So we can essentially, if we are able to do analytical differentiation, we can do this, except here the expressions are not generated. It's kind of a subtle difference. The expressions are not generated for the analytical derivatives, but rather the values of the derivatives, the relevant partial derivatives, are computed numerically, and those numbers are sort of carried around in some sense. And it turns out that carrying around numbers is much more efficient than carrying around expressions for derivatives, I guess. So that's kind of the idea. Um, and it's very fast and very efficient with modern implementations. It's faster than finite differences and certainly faster than analytical methods. It's faster than finite differences for large problems. It may not necessarily be faster for small problems. And it's very accurate. It's basically as accurate as analytical expressions, um, and and certainly much more accurate than finite difference approximations of derivatives. If you are familiar with neural networks, there is a thing in neural networks called backpropagation. Backpropagation is essentially one way of doing automatic differentiation, which is propagating derivatives. I said if f consisted of a sequence of lines, we can propagate derivatives from line to line to line. Backpropagation is just one way of propagating derivatives in neural networks. It's just a special case of automatic differentiation, and I will provide an example later on of how say automatic differentiation will work. Okay, so having said that, well, actually, here's the Wikipedia page on the topic. If you have some function y, which is a function of g, which is a function of h, which is a function of x, then if you want to differentiate y with respect to x, you would just propagate the partial derivatives through this chain of function evaluations. So dy by dx will be all these sort of, this is essentially implementing chain rule. The only difference between this and analytical is that the sequence of sort of chain rule operations is computed in a highly efficient manner, taking into account the dependency graph, sometimes called the computational graph, of which variable affects which intermediate variable and so on. So those things can be taken into account in a highly efficient manner. And secondly, no explicit expression is carried around. Just numbers are carried around, and numbers are much lighter weight than carrying around analytical expressions. Okay, so we will now see demonstrations of all three methods of differentiation quickly.